So let me continue the lecture. So here now is a, I forgot to share screen, I think. Good thing I remembered, otherwise it would not have been very good for you. Share screen. So now comes the model that we used in our analysis. So the first thing we did was to divide the community into different age groups. And how did we do that? Well, we went to a study on community behavior, which by now is of course 14 years old, but still believed to be fairly well fitted to reality. And that is where they have followed people to see who they have contacts with. So they divided people into 6 different age groups. I think it was infants, young children, teenagers, young adults, and senior adults, sort of those age groups. And then from this sociological study, it was found out to what extent people in the different age groups, who they mix with. So maybe young school children mix much with other young school children, and possibly also with people in the parental ages, but less so with people between 20 and 30. And senior people maybe mixed quite a lot with other senior people, but also with people in maybe middle age, because that could be their children or something like that. So this we did first, and there we took the rate at which different age groups mix with each other. We took from this earlier study, which is sort of the standard reference in this area. But on top of that, we divided individuals of each age group into 3 different activity levels. So we assume that within a certain age group, all individuals are not identical. We have a large group of normal people or normal activity that have normal activity level. We assume that 50% belong to this group, and 25% are slightly less social, and for them we assume that the activity level was half of the normal one. And then we had a high activity group, and that group consisted of 25% of the community, and their activity, the rate of contact was twice as big. So in some sense, this captures features of a network, in the sense that some people are more socially active, they have more contacts, and others are less socially active. So we had 6 age groups and 3 activity groups within each age group. So in total there were 18 different groups, and R0 is, as I described in a previous lecture, is the dominant eigenvalue of this next generation matrix. And if you have this model, you can compute the final size equations numerically. I will not present how that is done. Then we also inserted preventive measures and restrictions, and we did this rather in a simple form, in the sense that we assumed that all mixing rates were reduced by the same factor. So all individuals in different age groups and also in different activity levels reduced their contacts by the same factor C. Consequence of that is that the effective reproduction number before disease spreading is the original one multiplied by alpha. So if alpha is smaller than 1 minus 1 upon R naught, then the epidemic will stop. So the first situation is where we consider these restrictions to apply all through the epidemic. So already from the start, the preventive measures or the restrictions were put in place, and they were kept all along until the epidemic stopped. Then we get explicit final size equations that we can solve numerically. And the question that we addressed is the following. What is the smallest value that gives herd immunity after the outbreak is over? What does that mean? Well, if alpha is 1, that's not at all a very small value, then there is no, the effective reproduction number is the original one, and you see a big outbreak. And then after that outbreak, if you lift restrictions, you will not see a second wave clearly. On the other hand, if alpha is very small, maybe if it's small enough, the effective reproduction number will actually be below 1. So then there will not be an outbreak when restrictions are put in place. And if you then lift restrictions, there is clearly a chance for an outbreak taking place. So the question is, what is the smallest alpha for which after the first outbreak has taken place, there is no risk for a second outbreak if you lift the restrictions? So suppose the outbreak with preventive measures alpha takes place, then we lift preventions, so we bring back alpha to 1. Then the question is the population at risk for a second wave? But we're not really interested in the value of alpha. What we're mainly interested in is then what is the overall immunity level for that particular threshold alpha star. And that is what we investigated numerically, and we came to the following table. So depending on the original value of R naught, remember now that we have 6 different age groups, we have mixing rates between the different age groups, and then we have social activity within each age group. And then let's focus on the mid one, which is considered to be fairly realistic for at least the Stockholm region. Then here on the right is the classical herd immunity level, and that is 60%, irrespective of what type of population structure we consider. Whereas if we take the situation where we both have age groups and activity structure, then the disease-induced herd immunity level is 43%. So this means that if we reduce preventive measures such that if we did nothing, we would have more than 60% getting infected. But if we insert preventive measures such that, to that extent, such that 43% get infected, if we then lift restrictions, the effective reproduction number will be exactly 1. So that there will be no risk for a big second wave. So 43% is enough for herd immunity to be obtained when it is disease induced. So a fairly big difference, 60% versus 43%. In situation 2, we looked at more realistic situation, but of course solutions can only be illustrated by diagrams. So we looked at the following situation. The epidemic started February 15. We used a deterministic SCIR. And then 1 month later, restrictions were put in place, and we considered 4 different values of alpha. And then June 30, all restrictions were suddenly lifted. What would then happen? Well, that depends on what restrictive measures were put in place. And here are the curves. Here we have incidence. So, well, it's incidence or the current number of infectives. And the blue curve is if we did nothing. So we see we would have a very big outbreak, which quickly dies out. So after, seems like around 120 days, after 3 months, the epidemic would have stopped. And a big fraction would have gotten affected. On the next slide, we see what fraction. If we have some small restrictions, we have a smaller outbreak, and it dies out rather quickly as well. So we see that the change here is after 30 days, and that coincides with that after 1 month we put in restrictions. June 30 we lift restrictions, and that is 3.5 months later. So we see that is here, and it is around 135 days. If we have fairly strong restrictions, we see we have a smaller outbreak, and then when restrictions are lifted, we don't have a second wave, but at least it is prolonged before it starts dying out. And if we have a very severe restrictions, you might call it lockdown, then we have a very small outbreak, but once we lift restrictions, we have a second wave. So on the next slide, this is incidence, but on the next slide we see the cumulative number of cumulative fraction of infected. So we see that the biggest outbreak is if we do nothing. Second biggest if we have very small restrictions. But rather surprising, if we have a severe lockdown and then suddenly lift things after 3.5 months, we will actually have more people infected as compared to if we have less severe lockdown and lift restrictions at the same time. Of course, they have not completely stopped yet, so maybe we should have made the figure slightly longer, but they do stop more or less at these values. We also did the same thing if we had gradual exit during the summer. So as before, we insert measures momentarily, March 15, but then we lift preventive measures gradually during the summer. So you sort of linearly we lift restrictions starting June 1st and ending August 30. Then the corresponding curves look like this. So also here, the lockdown has a slightly bigger outbreak, but if we lift things slower, these two curves will coincide. So the main conclusion from our result is that disease-induced herd immunity is substantially lower than the classical one. So many people have said that herd immunity, also me by the way, the herd immunity level is about 60% for COVID-19 in Sweden. I don't believe this to be true anymore. I think it is rather between 40 and 45%, but I don't claim to know this number. So that needs to be investigated. Okay, how about our model? It was not completely realistic. What if we include also other heterogeneities such as households, schools, workplaces, and spatial effect? Then I think most of these things have the effect that the difference between classical herd immunity and disease-induced herd immunity is actually bigger. So that would make the difference even bigger. However, the same does not apply to restrictive restrictions and preventions. In particular, it was assumed that all groups reduced their contacts with the same fraction, with the same factor. And this might not be the case. For instance, it could be that highly socially active people reduce their contacts by a bigger factor than less socially active people. You can also think of that school closing affects mainly people in high school, so they reduce their contacts more than younger children, for instance. And also 70 plus people have been encouraged to isolate themselves, so maybe they reduce their contacts to a bigger extent. So what happens then? That is a more complicated situation that we have not studied, and I don't even know the overall effect of that. So to end up, some important research questions for COVID-19. I think this is a good formula that the current effective reproduction number is the average number of infectious contacts that those who currently have been infected would infect, multiplied by the effect of their preventive measures, multiplied by the fraction that is susceptible among uh, those being contacted from the current group of infectives. So you can call this the potential, you can call this the effect of the preventive measures, and you could call this factor the effect of immunity. So an important question is, what is the current potential? If it was 2.5 for those getting infected early on, is it now maybe 2, or is it bigger or less? And then what is the effect of various preventive measures? So this C of T is somehow the overall effect from many different preventive measures. So what happens if you relax one preventive measure? What happens with C? And how do they add up? For instance, if you have two preventive measures, it's not clear to me that if one has effect 10% and the other one also has effect 10%, it's not clear that if you do both, the effect will be 20%. Maybe they overlap somehow. And also, what is the current immunity level? Well, that can be estimated from data, for instance, by antibody testing, but I think, well, some people claim that there is T cells that might give some type of immunity, but I think also the susceptibility among those that have not yet been infected is probably lower, because the highly susceptible people have already been infected, so there could be a group of people that have a very hard time to get infected for various reasons. So to sort of quantify that in a good way is an important question as well. Okay, this ends today's lecture.